This is the digital circuit class. And we are, where are we? We're in chapter 13. And we're going to be done in about 15 minutes with this chapter because it's so pathetic. So, we have shift registers. I don't know why we need them, but you will. Shift register. So we could have a shift register right, or we could have a shift register left. So the issue is, I have, we'll go with 4 bits of data. I have 4 bits of data, and sitting there, we'll call it A0, A1, A2, A3. And I got 4 pieces of wire, and I'm going to send those parallel-wise into a new place. Boom, 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 boom. All right, no problem. Don't need a shift register. But if I have 3 bits of data, we'll go with 4. 4 bits of data, A0, A1, A2, A3. And I only have 1 wire, like to a printer, for example. Then how am I going to get the data to the printer? Well, I have to send the data 1 bit at a time is all I can send. So I use a shift register, so I got a 1, 0, 0, 1, and I use it and I send a 1 to the printer, and then I shift everything right, and then I've got that. And then I've sent a 0 to the printer, and I shift everything right, and I have that. And I send a 0 to the printer, I shift everything right, I have that. And then I send 1 to the printer, and now I've sent the entire word down that serial cable. So in a communication setting, when we're talking serial communication, which means you're on the phone talking, you have a data stream going across a DSL line, that's all serial, right?
So you start with the least significant and working your way to the...
Unless I'm doing a left bit shift, then I'm going the other way. But I chose a right bit shift, which means the right bit drops off. But you know, I could decide to write a system that sends the most significant bit first. But I'd have to tell the printer that I was sending it to that I was doing it.
Let's not get too confused.
Yeah. So anyway, so we see that we can in fact shift things in and out. Now, we're going to use it next semester, a shift register. Okay, so what we're going to do next semester is that we've got buttons, and we got a 5-cent button, and we got a 10-cent button, and we got a 25-cent one, and we got a 50-cent one, and we got a $1 one. And then we got another button for Coke. This is Coke. And another button for Diet Coke. And another button for Cherry Diet Coke, etc. And then, well, this is money, and that's not money. And then when I give the money, I'm going to have the money using bits 0, 1, and 2. And I'm going to give 5 cents or 10 cents or 10 cents or 25 cents when I give change. All right? But when I give the product, I'm also going to use 0, 1, 2, and so on, 3. And 0, 1, 2, 3, 4, 5. So I have bit 5, 6, and 7 that I'm using to store what product you ordered. Well, I'm going to use a shift register to shift that 5 times until it's in position 0, and now the Coke is given out. So I'm going to write you're going to write a program where you're actually going to do that in a shift register. Okay. I look on page 630, and I see a shift register being used, and it's recycling. And no, it's just a shift register. I have a serial bit going out on the right-hand side, and every time the clock pulse happens, I get another bit that leaves. But whatever happens, whatever's in Q3. Whatever's in Q3, when the clock pulse happens, goes to Q2. Whatever in 2Q goes to Q1. Whatever's in Q1 goes to Q0, and the guy in Q0 goes away because he's the serial output. So I end up shifting my data to the right. You could have a situation where you have parallel ends. I'm on page 632. I have a parallel end signal. I have a serial signal coming in through serial DS over there on the left, and I bring it into my flip-flops, and then I take it out as a parallel output. So I can do that. Then on page 633, I have Johnson shift counters, and I have ring shift counters. So ring shift counter, ring. Somebody's going to be high, and then somebody else is going to be high, and then somebody else is going to be high, and then somebody else is going to be high. So that would be a ring counter. Where would I use something like that? Well, I'd use it on my, who's the idiot that made that line? I would use it on something that, where I'm selecting the CD, and I'm selecting the hard drive, I'm selecting the 5 1/4 inch floppy, 5 1/2, right? 5 1/2 inch floppy, and the 7 inch floppy. And when they're turned on the address bus, I'm selecting them to have their turn. Okay, so I've got a ring shift register that's only selecting one thing at a time. Okay, so I've got some anti-aircraft guns, and I've got some 16-inch main guns, and I have something else, and I'm shifting from my thought pattern from one armament to another as I fire this one, and then I fire that one, and then I fire the other one. Token rings were the same type of thing. We hook up computers, and we put them on a token ring, and now I pass a token from this guy to that guy. He's next. And then I pass him to him. He's next. And then I pass him over here. He's next. The guy over here has to wait. Has to wait until it gets over to him. If the guy over here wants to talk to the guy over there, then he's got to send a message. Got to go all the way around the ring and get to him before it gets to him. Okay, just the way it is. And then Johnson counters are a little bit different. We end up being, oh, I forget. Oh, there it is. No, that's the ring counter. Where's the Johnson counter? Oh, there's the Johnson counter. Yeah, I got it. Page 634, I got a Johnson counter. I don't know why they call it a Johnson counter. Don't bother to ask. All right, so I got something like that, and then I got something like this, and I got something like that, and then I got something like that. And didn't you go and build one of those? Here, didn't you have a flashy light soldering project this semester at the beginning of the semester to put together? Yeah, that, if it worked, it was a Johnson counter. Okay, so if it worked, all right. So we can do shift registers. Okay, so now I can have on page 638, I can have the shift registers as a 7400 dual input chip. So I can have an IC chip that has one on it, and it'll go right, it'll go left, it'll do a parallel in, it'll do a parallel out. It'll do all those things just by selecting things for it to do. So now that leaves me plenty of room on the next test to have some, you know, who's on Q2. There's on page 644, there's a 74395 chip, 4-bit shift register with a 3-state output. What the heck is a 3-state output? Okay, somebody name a state. Yeah. Somebody name a state. Go ahead. Tell me a state.
Oh, God, there's so many.
There's Alabama. Okay, how about another one, another state? Colorado. Okay. Unfortunately, this is a digital circuit class, so our states are on, our states are off. What's the third state?
Pardon?
What is if our states are on and off, what's our third state?
Vote.
Neither on or off?
There's no third state.
Well, on page 466, it says 4-bit shift register with 3 state outputs. Right there, bottom of the page.
Yeah.
So there has to be a third state. If there's going to be, if you have a 3-state output, there has to be a third state. And so on, off, and high. High?
No change, brother.
High. High impedance. High impedance. Okay, so, yeah, so if I'm on, what do I have? 5 volts. If I'm off, what do I have? 0 volts. If I'm high impedance, what do I have?
Above 2.5, I guess.
No current. So if I'm off and I'm at 0, I can have current flowing to that 0, right? And turn on an LED. We've already done that, right? And if I go on, I can have current going because I have that 5 volts, and I can have current flow. A high impedance state means I'm not allowing current to flow in, and I'm not giving you any voltage out. Okay. So again, if I have a CD-ROM and I've got RAM and I got ROM and I've got a hard drive, then I can get data, and the data can send stuff in on any of those guys' data buses, but I only want it to go to one of them. So one of them is receiving the data. The other 3 are in a high impedance state, so they're not interfering with the data bus. Okay, three states. All right. Are we done with this chapter yet? Yeah, I think we are. Oh, no, we're not. Stepper motors. All right. That was silly. How to get rid of that? Anyway, so now we have a situation. Motor, yes.
How do you identify what symbol, what number you use to signify high impedance? 0 is off, 1 is on. High impedance is,
High impedance.
there's no.
No, there's no number.
Is there
No,
a readout? Just, I'm just making sure.
Yeah,
I'm
no.
missing something, I'm missing
no, you're not missing anything yet.
Who's the readout?
Huh? Yeah, high. Impedance. Yeah. That's all it is, yeah. All right. So now we have many different types of motors. So our normal, everyday swimming pool motor. What is it?
What?
Swimming pool motor. The motor on your swimming pool that pumps the water around.
It's
It's like blowing into a
Well, yeah, the
straw.
pump is the pump, but what makes the pump go roundy-roundy? It's a normal induction motor. Induction. And next semester we get to talk motors in detail. Now we're just going to talk about them in general. So it's an AC induction motor. You can also have AC motors that are synchronous. CHROUS. Synchronous motors.
synchronous, new word.
No, synchronous isn't a new word. The way I have it,
You can't spell it.
the way it's spelled might be new to the class. But so in an induction motor, what's happening is that I have if I'm 3 phases, I got phase A, phase B, phase C, and then I've got a rotor in here, and I'm inducing voltages on the rotor. There's no wires hooked up to the rotor at all. I'm inducing voltages by this changing magnetic field caused by the 60 cycle AC power. In a synchronous motor, what I'm doing is I'm putting a plus or minus charge on that rotor. So now I actually have a magnet that I'm causing in the rotor. It's going to rotate at the same frequency as the 60 hertz is rotating around here. So that's what it's going to do, and it's going to follow it exactly. And the power created will be caused by the degrees of difference between where the magnet is and where the magnetic field is. And if I try to put too much torque, it's going to slip a pole, and that's going to be catastrophic. But a induction motor, we might be running around at 1800 RPM around these three phases. It may only be running at 1400 RPM. And its torque is caused by that difference in the RPM. So something that's very lightly loaded will be very close to the speed of the AC stuff going around the motor. So as I load down the motor with more load, there's a bigger and bigger slip between how the magnetic field is going around the outside and where the rotor is. And that's what causes me to have more and more torque. And then if I want something, if I have the motor I have on my pool pump, do I care where the pump is going as it goes roundy? Do I care if it's up or down or to the right or to the bottom?
No.
I turn it on and it starts rotating, right? Well, if I care that I'm here and I want to be there, or there and I want to be there, or there. Thank you very much, video, for showing this hand motion. So let's say that I got this motor, and I want it to be there, and I want to know it's there. And then I got this motor, and I want it to be there, and I want to know it's there. And I want to know all the difference in between, how I got from there to there. And it matters to me the position of the motor. So give me an application where it might matter to you the position of the motor.
It's rotating regardless what position it's in.
Okay, for the robotic majors in the room, do you care where your robotic arm is, or does it just swirling around randomly is perfectly okay? It matters to you. Okay, so yes, it matters to the robotic majors where the damn robotic arm is. Okay, so they can't just go and take an induction motor that's rotating at 1800 RPM and stick it there and have it turn that robotic arm and then might go a little faster, a little slower because it's loaded. That doesn't make any sense. They want it to be at the right place at the right time every time, not someplace else. Okay. Yeah. So they're going to use a stepper motor to get it to where it's supposed to be, and they're going to be using encoders and to get it there, to tell it to get there. And now that robotic arm is going to go there and pick up something, and it's going to move over someplace else and put it down, and it's not going to lose a beat, and it's going to do it for 24 hours for 365 days in a row for 20 years without anybody doing anything except changing the oil every 5 years or so. And so now the issue is, how do we drive a stepper motor? So page 652, and we see that a stepper motor has a bunch of coils, and it has a rotor on the inside, and depending on which coil I energize, the north-south coil I energize, will depend on how it lines up. And I can make it so that I can do it in 45-degree increments, or I can do it in 10-degree increments, or I can do it in a half a degree increment. Whatever I need to do to get the precision that I want, I can make a stepper motor that way. So now I see on page 265 that if I go and energize those coils 1 0 0 0 1 0 1 0 0 0 0 1 0, I rotate clockwise. And if I energize those coils 0001, 0010, 0100, I see that I can rotate this guy counterclockwise. So depending on, if I look on the picture on the top of page 652, I see that there's only one set of coils that are closest to the next set of coils. So if I have the number 1 guy energized and I turn on number 4 next, it's going to rotate counterclockwise. If I have the number 1 guy energized and I turn on the number 2 coil next, it's going to rotate clockwise. Okay, and it's just going to rotate a little bit because I have what I have here. I'm going to rotate 60 degrees, it looks like, is what I'm going to do. And I'm going to do that every time. I'm going to go to the next step. It's a stepper motor. So now I need some digital circuit to do those steps to make the stepper motor move in the and bend to my will, so that it moves in the direction I want it to move when I want it to move. And of course, I'm going to do that with some higher level computer programming so that I don't have to worry about it. Yes.
So your stepper motor is bidirectional. You just, the shortest point from A to B is the direction it'll turn.
That's right.
Okay.
So it's going to be, it can go one way, it can go to the other way, but depending on who is energized next is how it's going to go there. It's going to snap into position. It's going to be there every time. Won't be a problem. The issue is, how do I make that happen? Because TTL Logic puts out all of 5 volts, and that 5 volts doesn't have much current behind it. This has to be a pretty small motor, and our robotic friends sort of like to have their robotic arm move something like 10 pounds or 20 pounds or 1,000 pounds. How are we going to do that? Well, on page 653, we have the TTL Logic, and we're using it to turn on a transistor, which is going to give us power. So that's how we're going to do that. And now I can buy a transistor that's going to be able to put out 1,000 amps if I need it, or a half an amp if I need it, whatever. Not the piddly 5 milliamps putting out on TTL Logic. So I have a way to do that. Now, our current printers are using a stepper motor to get the ink from one side of the printer to the other. That's how I'm doing that. That's how it knows it's here, and here I'll show you, here and not there. Because the stepper motor is moving it, the stepper motor is going to get it to the right spot every time. I count 10 steps, it moves 10 steps, period, the end. Okay. Page 655, and now we're talking about tri-state buffers on page 656, 657, octal latches and flip-flops. What's an octal latch anyway?
8 latches.
Okay, an octal latch would be 8 latches, right? So like, yeah, 8, octal. I thought it's an octopus or something, and we went out there and grabbed the other. Yeah, 8 of them, yeah. 656, tri-state buffer. It's going to be in a high impedance state, it's going to be on, it's going to be off. That's all the only choices you have. I think we ought to be done with this chapter pretty soon. Nope, all done. Set of vocabulary words. Anybody got a syllabus so I know what homework I'm doing?
I do actually.
Oh, I have one. I found it. I found the homework. 13.1. 13.1. In figure T13.1, will the data bits be shifted right or left to the clock pulse? Will they be shifted on a positive or negative clock? All right, so we'll look at positive or negative clock. Okay, so I look over there. Oh, look at that, negative clock pulse. So the B part of the answer is negative clock pulse. Okay, the A part of the answer. Am I shifting right or am I shifting left? And when the clock pulse occurs, whatever in Q3 is going to Q2, therefore I am going in the right direction. Okay, by the picture, so I'm going right. Oh, excellent. Next problem. 13.6. Back to figure P13.1, and we're going to do a parallel to serial converter. Where are the data lines, the data input lines, and the data output lines? Okay, so we'll go with data output. Okay, so where is it? That's at Q0 is my data output. Where is my data input? I don't hear any answers out there. D3, D2, D1, D0. So that's my data in. Oh, look at that. It's even marked input in the drawing. Isn't that lovely? Thank you, author, for marking that for us. Okay, 13.9. 13.9. Went too far already. Has to go back. How many flip-flops are required to produce the waveform shown below? Okay, now, this particular question will be on your next test because it's an easy one and simple for me to put on the next test. Okay, how many flip-flops? So we got the clock pulse doing this. So this is the clock pulse. And 0, 1, 2, 3, 4. And then we have the Q doing this. Up at 2. Down at 5. Down at 3. Down at 3. Up at 5. That's pretty bad. So how many are we going to need to make that particular pattern? Okay, well, if we have one flip-flop, all right, so I got one flip-flop. One flip-flop. What can it do? All right, so it could be high, and then it could be low, and then it could be high, and then it could be low, and then it could be high, and it could be, so I could have something like that, right? So basically, one flip-flop, I'm dividing by 2. Okay, what if I have 2 flip-flops? Well, I could be high, and then I could be low, and then I could be high, and then I could be low, and that would basically be a divide by 4 guy of the clock. If I had 3 flip-flops, I could be high, I could be low, and I could be high again, and now I've got to divide by 8 going on. Okay, so I go low, and I stay low for 1, 2 clock pulses. I then go high, I stay high. Okay, so from the time that I go low the first time on Q to the time that I go low the second time on Q, I use 3 clock pulses. Can I go 3 clock pulses with a divide by 2? No. Can I do it with a divide by 4? Yes. So if I had a divide by 4 going on, and when I got to 3, I reset it, right?
No idea.
So if I go 0, 0, 0, 0, 0, 1, 0, 1, 0, reset 0, 0, 0, 0, 0, 1, 0, 1, 0. I could do that in 2 flip-flops. So it would take 2 flip-flops to do a divide by 3. Okay, so I got 2 flip-flops, and I'm resetting right here. Boom, 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 boom. That's what I'm doing. Okay, good enough? No? Okay, do it again. Huh? What? I'm going to do it again. I got a clock pulse. And I got some flip-flop that's going to change on the negative clock pulse. And I got one of them. I got one flip-flop. Okay, so I can go, and I can be high, and I can go low, and I can go high, and I can go low, and I can go high, and I can go low, and I can go high, and I can go low. I basically done a divide by 2 of the clock. Okay, now I got a second flip-flop. Okay, and it's basically gonna use the first flip-flop as its clock, and it can be high, and it can go low, and it can go high, and it can go low, and now I get a divide by 4 of the clock pulse going on. All right, so, but with 2 flip-flops, I can have a reset happen at 3. Okay, where's 3? There's 4, there's 1 and 1 is 3, right? So I'd have a reset, 1, yeah, 1 and 1 is 3.
Oh, binary.
Yeah, binary, 1 and 1 is 3. So I reset at 3, right? I go up. Yeah, I go up because now I stay up. And there's 3 again. I reset. And now I've got something that is a divide by 3 counter. Right? Do it again?
Well, so the second flip-flop on the first, like, does the first flip-flop act like a gate? To the
Yeah, the
ball?
first flip-flop is being used to clock the second flip-flop. Exactly.
Okay.
But it doesn't have to be used as a gate to do the second flip-flop.
No, it was set.
But it changes on the positive side of the first flip-flop?
No,
That's
right
the
here.
right-
Negative,
that's right.
negative side right there.
Yeah, that's the negative side of the.
Oh, did I do it in the wrong spot? I did.
Yeah.
Yeah, stupid me. Alright, so you want me to go down there and up there and down there and up there. Is that better?
Now we're talking a whole different thing.
Alright,
Okay.
so here's 3. There's 3. Boom, boom. There's 3. Here's 3. 3, 3.
Reset's gonna be
Boom,
1,
boom. So it goes
2, 3, no, yeah.
reset, goes up, blah, 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 down, down in 3. Boom. And now, but in order to have 3 states, I need 2 flip-flops.
And the reset is in relation to the first flip-flop still? Or
Both of them, yeah.
Both of them?
Yeah.
So when they're both high, it resets
Yeah, you never see,
because of the
3.
Okay.
because of
You're never going to see the 3. It goes back to 0, 0.
I see.
Oh, let's see. Turn it back on. Okay, there we go. Now we're going again. Got rid of mom. 1318. Sketch the waveform of Q1 to Q3 for the 74194 circuit shown in P1318. Also list the operating mode at each positive edge trigger, clock edge. Okay. And this is exactly the type of problem that's going to be on the next test too, so that'd be pretty cool. Okay, so we've got this clock pulse. Let's see, how many do I need? 9. 1, 2, 3. Do I start at 0? So I'm at 4, 5, 6, 7, 8, 9, 10 because I started at 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And things are happening on a positive clock. And then I've got a master reset that's knotted. So it's going to go high before the first positive clock. It's going to go and cycle between 5 and 6. 5 and 6. And then it's going to go high the rest of the time. Okay. And then we got an S0 and an S1. All right, so the S0 is going to be high, and then it's going to go low until the middle of 3, and then it's going to go high the rest of the time. And the S1 is going to be high until just after 2, and then it's going to cycle up during 5, down in 6, up and down in 8, and up after 9. And then we're going to put in our, we'll use those guys. And so oh, that's really bad. All right, well, I guess that'll do. Okay, so that's making sure our things are in the right spot. Oh, that's pretty good for drawing. All right, looking good. And what we want to know is what is Q0, Q1, Q2, and Q3. All right, that looks good. The reset is low, that makes it high, so all these guys are going to start at 0. Okay, so we're going to, oh shit, didn't want to do that. What did I want to do? I want to go in, I want to make it bigger. How is it gonna let me make it bigger? It's not gonna let me make it bigger. All right. Are we using those guys? Where is it? What are we using? These guys. Those guys. Okay, there we go. So we'll just 1, 2, 3, 4, 5, 6, 7. Thank you very much, computer. All right, so we got everything marked for when the clock is going to happen. Delete. Where's the delete button? Boom. Okay. Back to what we're doing. And the master reset happens. It went low, which means it goes high, and the master reset occurred, and everything is low. Low, 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 low. Everything's low. Okay. Now, the master reset occurs again between 5 and 6. So between 5 and 6, we're going to see a low, a low, a low, and a low. All right. So we're all happy with that? Yeah, almost done. All right. Now, 74, 194. Where, we got to go back to the page that has it, 74, 194. 74, 165. Is it a 164? It's a 194? 194. All right, 194. Shift registers. There we go. 74, 194. I found it. Page 641. Okay? And it says when both S1 and S2 are high, nothing happens. Okay, so S1, S0. 1, 1, nothing. Okay, S1, S0. S1, S0. When, actually those are lows. That's an L for low, not a 1 for 1. All right, so when there's 0, 0, nothing happens. When it's high and low, I shift left. So 1, 0, I do a left. 1, when I'm 0, 1, I do a right. And when I'm 1, 1, I do a parallel load. Okay. So we're going to translate that into English, and we're going to call this guy 0. We're going to call this guy a 2, that guy a 1, and this guy a 3. Okay. So I look at these guys, and they're both high, 1 and 1. So this is going to be a parallel load. Parallel load. I have S0 as low, S1 is high, so this guy is a left. This guy is a left. They're both low, so that's going to be a hold. Hold. Nothing's happening. Then this guy's going to be a right. Another right. Both of them happening, but they're both high during the master reset. So even though they would have done a parallel load, it doesn't matter, the master reset does it. So that's not an issue. This is going to be a right. This is going to be a right. This is going to be a right. And nothing happens in there because the clock pulse didn't happen when that thing went up and down. Okay. Got it? Okay. Okay, back to the picture. What picture is it? Okay, I got it. Okay, so the first thing that happens is a parallel load, and I see that D0 is a 1. So this guy's going to go high. These guys are going to stay at 0 during the parallel load. I'm going to do a left shift. And I see that when I do a left shift, I'm shifting left. I'm shifting in the 0. And I end up I do a left shift and I go to 0. I stay at 0, I stay at 0, I stay at 0. I do another left shift and I shift in another 0. Left shift. Oh, dummy. Good thing I don't have to erase everything. Okay, I do a left shift. The zero, Q0 goes to Q1. And the Q1 goes to Q2, and the Q2 goes to Q3. I do another left shift. I shift in a 0, and Q1 shifts to 0, Q2 goes high, Q3 stays at 0. I now do a hold, and nothing happens. Hold, 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 nothing happens. Then I do a right. And a right has the DSR as a 1, so I'm going to do a right shift. He goes high. The low from there goes here, making him low. The high from the low goes up. The low stays low. I do another right. I shift in a right. Shift in a 1. That 1 gets shifted. That's a 0. That gets shifted. That's a 1 that gets shifted. Okay, then the master reset happens, and everything goes back to 0. Then I do another right, which means I bring in a 1 from here. The 0 gets shifted, the 0 gets shifted, the 0 gets shifted. I do another right. Another 1 comes in, that 1 shifts. 0 stays the same, 0 stays the same. I get another right. I get a 1 coming in, the 1 goes up, the 1 goes up. I have a 0 there. Nothing happens here. I have one more right shift. I'm high, I'm high, I'm high, and that guy goes up and high. Ta-da! All done for 1 lousy point on the next test. So I can have a parallel load, I can have a shift right, I can have a shift left, I can change them in the middle of the stream.
What's the parallel load actually do?
It brings in all the data. Data 0, 1, 2, 3, and puts it at Q 0, 1, 2, 3.
Oh,
What was that, 18?
yeah.
28. How many clock pulses? Oh, okay. So this would be an easy one, right? 28. How many clock pulses are required at CP to cause the stepper motor to make 1 revolution in figure 1327? And now I gotta find figure 1327. 1328. Okay, so I got 1327. All right. So how many are required? How many clock pulses are required? 4. 4. Look on page 6. Yeah, 1327. Oh, 1328? I'm at 1326. 1327. No, I'm in the right place. 1327.
Yeah, the figure, there's 1327 figure.
Oh, it's on page 653. On page 653 shows a stepper motor. I do a 1, a 1, a 1, a 1. Going to take four clock pulses to shift 360 degrees. All right, enough? Do the multi-sim problems next time. Okay, no problem.